Have you ever stopped to wonder how you can have like a dozen browser tabs open, a video playing, and a game running all at the same time without your computer just completely giving up? It really feels like magic, doesn't it? But it's not. It's actually one of the most brilliant and critical jobs of your operating system, memory management. Today, we're going to pull back the curtain on this invisible process that keeps our entire digital world from crashing down into total chaos.
So take a look at this. We've got two programs here, Process A and Process B. Both of them need to live inside your computer's memory to run. Now, they each need their own space to work. But here's the catch. The total amount of memory is limited. So how does the operating system act like a traffic cop, making sure these programs stay in their own lanes and don't cause a massive system-crashing pileup? That is the fundamental puzzle we are about to solve.
All right, here's our game plan. We're going to tackle this in 5 key steps. First, we'll look at the memory puzzle itself. Then, we'll see how a program gets its home in memory, a process called binding. After that, we'll dive into the kind of mind-bending idea of 2 separate worlds, the logical world a program sees versus the physical world that actually exists. We'll meet the hardware hero that connects them, the MMU, and finally, we'll uncover a clever trick called swapping for when we just plain run out of room.
Okay, let's jump right into that first piece, the memory puzzle. You know, at its core, the problem is actually pretty simple. We have a finite amount of physical memory. Think of it like a single bookshelf. But we have a nearly infinite number of programs that all want a spot on that shelf, often at the exact same time.
Now, before we go any further, let's get one key term straight. When you double-click an icon to launch an application, you're not just running a program, you are creating a process. So a process is that program when it's live and in action, actively doing its thing on your computer. That's the living, breathing thing that the operating system has to manage. And right here, this is the fundamental conflict. Every single one of those processes, your web browser, your music player, all of it, needs its own protected slice of memory to work properly. It needs a safe space to store its data and run its code. But the physical RAM chips inside your computer have a hard, unchangeable limit. This clash is the entire reason memory management even needs to exist.
So how does the OS even begin to solve this puzzle? Well, the very first step is something called binding. You can think of it as the moment the OS gives a program an actual, physical address, a home, a place to live inside the computer's memory. Think of it like this. A programmer writes code using abstract ideas, right? Like, store this value in a variable called x. Well, address binding is the step that translates that abstract variable x into a concrete street address, like physical memory location number 74,014. It's all about connecting the code's symbolic world to the hardware's real physical world.
Now, this binding process isn't a one-shot deal. It can happen at 3 totally different stages. Really old systems did it at compile time, where the addresses were basically hard-coded from the very beginning. Super fast, but incredibly inflexible. A slightly better method is load time, where the address gets set the moment you launch the program. But the real magic, the approach that makes modern multitasking possible, happens at execution time. The address is assigned on the fly, while the program is already up and running.
And to make that amazing execution time binding actually work, the OS has to pull off an incredible feat of abstraction. It basically creates 2 parallel universes for memory addresses.
Probably the simplest way to think about it is that the CPU, where your program is actually running, and the physical memory hardware, well, they speak different languages. The CPU thinks in one set of addresses, and the memory unit operates on a completely different one. This separation, this gap between them, is the secret to everything.
Let's really break that down. The logical address is what the CPU creates. You'll also hear it called a virtual address. This is the program's point of view. As far as the program is concerned, it has its own private, clean stretch of memory, usually starting at address 0. On the other side, you have the physical address. This is the real deal address that the memory hardware understands, the hardware's reality. And here's the truly mind-blowing part. The program has absolutely no idea where it actually is in physical memory.
So the logical address space is basically the program's personal map of its own world. It's the entire universe of addresses it thinks it has access to.
And then you have the physical address space, which is the actual finite territory available on the real RAM chips. The whole critical job of the operating system is to constantly and instantly translate the program's make-believe map onto the real one.
Okay, so how does this translation happen? Instantly for every single time the computer needs to access memory? Well, for that, we need a translator. And that brings us to the unsung hero of our story. The Memory Management Unit, or MMU for short.
The MMU is an actual piece of hardware sitting right there with your CPU, and its one and only job is to be an incredibly fast translator. Every single time the CPU says, "Hey, I need the data from my logical address 100, the MMU intercepts that request, and in a flash converts it to, got it, that's actually physical address 50,100. And this happens at runtime for every single memory access.
To make this less abstract, here's a really simple way it can work. The OS basically tells the MMU, hey, for this process, its starting point in physical memory is, let's say, 50,000. That value gets stored in a special spot called a relocation register. Then, when the program asks for its own logical address, say 100, the MMU just does some quick math. 50,000 plus 100 equals 50,100. And just like that, translation complete.
The impact of having this MMU is just profound. First off, the program lives happily in its own little logical bubble, never even seeing the real physical addresses. This is what allows for that super flexible execution time binding we talked about, because the OS can move the program around in physical memory just by changing one number in that relocation register. And crucially, it protects processes from each other. My program can't go snooping around in your program's memory, because from its point of view, your program's physical address doesn't even exist.
Now, this whole system is amazing, but it still depends on having enough physical memory to go around. So what happens when we just run out? Well, the OS has one more clever trick up its sleeve. So picture this. You've loaded up a ton of applications, your RAM is totally full, but you want to launch one more program. The system doesn't just crash. Instead, it turns to a technique called swapping.
And swapping is, well, it's exactly what it sounds like. The OS can find a process that's just sitting idle in the background, copies its entire memory footprint out of that fast RAM, and temporarily park it on a much slower but way bigger backing store like your hard drive or your SSD. And just like that, a whole chunk of physical RAM is freed up for the new process you want to run. The really cool part about this is that the swapped out process can later be brought right back into memory to pick up exactly where it left off. Now, the biggest downside, of course, is speed. Transferring all that data to and from a disk is way slower than RAM. But don't think for a second that this is some old, forgotten technique. Nope. Modified, much more sophisticated versions of swapping are used in pretty much every modern operating system you use today, from Unix and Linux all the way to Windows.
So, when you put it all together, the logical addresses, the physical hardware, the MMU doing its lightning-fast translation, and swapping kicking in when space gets tight, you get this elegant, invisible system running behind the scenes. This is the absolute foundation that makes everything you do on your computer possible, providing the stability and the flexibility for true modern multitasking.
And that leads to a final thought for you. This core idea, this virtualization of memory, is almost 60 years old. That's a huge testament to just how brilliant and timeless the design is. But as our computing needs keep evolving, with AI, with massive datasets, with new kinds of hardware, you have to wonder, what will the next revolutionary leap in memory management actually look like?